Hello everyone, my name is Leonardo and I'm going to present a fault injection framework for real-time multicore embedded systems. This work was developed with my advisor, Professor Dr. Antônio Augusto Frohlich, in the Software Hardware Integration Laboratory at UFSC. The main motivation for this work are the digital twins currently being fostered on the industry. These digital twins aim at working as a virtual substitute of real-world subjects that are built around models. Therefore, the utility of such digital twins is related to their capacity to mimic the behavior of such subjects in the real world. Moreover, for their application on critical CPSs like e-medicine or autonomous vehicles, it's necessary that those digital twins can simulate the behavior of the various components of these CPS in order to achieve the desired level of test coverage. In this context, we propose a framework for fault injection that is able to perform a fine-grained behavior simulation of the various components of a critical system. The fault injection framework proposed in this work builds upon a non-intrusive monitoring system introduced by the authors on a previous publication. This monitoring system is part of a scheduling framework that supports the design of domain-specific low-overhead resource schedulers for critical systems. The main constructs of the monitoring system are the monitor and the clerk. The monitor provides the user with a powerful runtime engine to collect data through the clerks. It instruments the scheduling at compile time with sample operations at predefined interest points that are scheduling operations like thread dispatches. Also, during runtime, it automatically timestamps the sample data. The clerk provides a common interface to the different data sources available on the platform, such as the OS variables, hardware counters, and sensors. The monitoring system non-intrusiveness is essential to guarantee the confidence and reliability for the generated models and tests that use runtime collected data. We achieve non-intrusiveness with a set of design choices and its implications. The monitor uses fixed data structures that are defined at compile time. The monitor initializes along with the OS boot. The sampling operations is homogeneous. The code is generated with templates that are solved at precompile time, thus every data capture executes the same code. The checking time of the condition to execute the capture, which means that the sampling frequency has been achieved, is constant. The data processing is done on idle time or after the system execution is finished. As the operation time of the monitor is constant for every single capture, we consider jitter to derive from the fact that a capture is done or not. Fault injector is modeled as a component of the monitoring system. It can operate on two different modes: fault injection by methods, where non-fault behaviors such as staccato or drift can be implemented as algorithms that will aggregate the data sampled by the monitor, or fault injection by behavioral simulation, where the data sampled by the monitor is substituted by the data on a previously collected OSINTEtic trace. A trace is considered to be a set of samples S, where each sample consists of the values of the any monitored variables on the system collected on the same system moment. Fault injection mode and its parameters are defined at precompile time. The injection of faults is done on the behalf of the monitoring system data sampling, using the method inject. Fault injection can be enabled or disabled at any moment of the execution by using the method setEnable. The initialization of the data structures of the fault injection is done at boot time with the method config, which is performed along with the monitor initialization. By design choice, the fault injection starts disabled. A particular attention is given to cumulative variables. These variables accumulate their value during all the execution of the system, and typically are used to count the number of occurrences of a given event, such as committed instructions, cache misses, or deadline misses. When we are injecting faults to these variables, it's not enough to just change their value on the buffer of the monitor, since the next time this data is sampled would generate a disruption on the system behavior, once the value sampled will not be consistent to the value stored on the buffer. Therefore, it's necessary to update the data source of cumulative variables whenever we're injecting faults on them. Respecting the design principles, this process must be abstracted by the clerk and it's done through the method write, which is called by the monitor via the method inject whenever a fault injection is conducted. To avoid disrupting the behavior of the system, it's necessary that the fault injection process is non-intrusive. The non-intrusiveness of the fault injector relies on the non-intrusiveness of the monitoring system. Plus, there are some design decisions and implications that helps to build a non-intrusive fault injector. The data structures are configured during the monitoring system initialization, which occurs during OS boot time. Fault injection mode is fixed and defined at compile time. Fault injection mechanism is homogeneous. Every injection executes the very same code. Fault injection operates on the behalf of data sampling. Thus, we consider jitter to be the same condition as the applied on the monitor, and be directly dependent on the fact that the fault injector executes or not. For the experimental setup of this paper, we chose to work with a Raspberry Pi 3B, which features an ARM Cortex-A53, a quad-core of 1.2 GHz, a 1 GB RAM memory, 16 KB of level 1 cache, and 512 KB level 2 cache. This platform was mediated by EPOS, the Embedded Parallel Operating System, in its version 2.2. The benchmark that was set to run on this platform was Disparity, which is used for cruise control, pedestrian tracking, and collision control on autonomous vehicles. The benchmark was presented by the San Diego Vision Benchmark Suite on Venkar et al. 2019. The fault injection was evaluated on 5 different configurations of sampling rate, going from 10 Hz to 200 Hz frequency. The task set was configured to execute on cores 1, 2, and 3, since core 0 is considered to be reserved for control operations like alarms and interrupt handling. The task set is presented on the table and configures a 27% utilization on each of the cores. To depict the fault injection capabilities, we choose to monitor a typical set of performance counters composed of committed instructions, level 1 data cache misses, branch mispredictions, level 2 data cache hits, level 1 instruction cache misses, and branch instructions retired. Such counters were applied on works like Vu and Taylor, Rai et al., and Nath and Mahapatra. To simplify the visualization, the sampling rate was set to 50 Hz, and the fault injection was only enabled on the period between 2 releases of the model tasks. Fault injection operated on behavioral simulation mode by injecting a set of some samples of the bandwidth task that was previously captured running on the same platform. In this slide, we can see the impacts of fault injection on 2 of the selected performance counters, committed instructions and level 2 data cache hits. It's important to notice that besides changing the behavior of the system on the period between 2 executions of the selected task set, the fault injection does not change the behavior of the system during the execution of the tasks, period in which the fault injection was not enabled. To assess the overhead of the fault injection framework presented in this paper, we measured the monitor activation time on 20 different executions, with and without fault injection. The fault injection was evaluated on the behavioral simulation mode and was enabled during all the execution time. The table below presents the average observed overheads for each one of the sampling rates. It's possible to notice that the highest average overhead was at 0.1% for 200 Hz sampling rate. Following the same strategy, we also verified the fault injection overhead over the monitor. The table on the top of the page depicts the average overheads observed for each one of the sampling rates. The highest observed average overhead was 24.71%, which besides seeming a little bit high, is applied on a 0.1 original overhead over the system. On the table on the bottom of the slide, we present the average overhead of the float injector over the application, where the application time is considered with the monitor active, and the float injection was only enabled to measure the overhead. It's possible to notice that the highest overhead observed is an average 0.1%. To assess the jitter of the proposed float injection framework, we use the same activation times obtained for the overhead calculation. The table below presents an evaluation of the jitter in terms of average jitter, maximum jitter, and standard deviation for each one of the sampling rates. It's possible to see that the highest average jitter is 5 microseconds. The maximum observed jitter is 19 microseconds, and the maximum standard deviation is 2.55 microseconds. Let's make a mathematical analysis of the results in terms of overhead and jitter. Let T be the set of the n measured activation times. Then, the system overhead θs is defined as the sum of all the activation times Ti, where Ti is in T, and Ti is the time the system spent on the IF time it passes on a point of interest. In case the monitor does not collect the data, the activation time is reduced to the condition verification time, which can consider to be 0 microseconds. In this way, the maximum jitter becomes equal to the maximum activation time, and the average jitter is calculated by dividing the float injection overhead by the number of data collection requested during the system execution, which is equal to the fraction of θs divided by n. Similarly, the average job activation latency alpha job is the result of the division of the total float injection overhead on the application, theta A, by the number NA of data collections requested during the execution of the jobs. The overhead on the application, theta A, can be calculated by the sum of all Ti in Ta, where Ta is a subset of T in which all Ti's occur during the execution of the application. As our final remarks, float injection can be used to train and assess the performance of fault-tolerant mechanisms, such as intrusion detection systems. The behavioral simulation capacity of the proposed float injection framework can be applied by digital twins to verify the behavior of systems actuators in fault conditions without incurring in any damage to the platform. As an example, the figure below depicts a scenario where a thermal cap mechanism should reduce operating frequency whenever the reserved temperature reaches 68 Celsius degrees. Our fault injection could be easily applied on such scenarios by overriding the sampled value on the monitor buffer. With this, we finish our presentation. Thank you for your attention, and I'll be available to answer any questions.